Okay, we're back. And before we get started with the Chapter 16 lecture, there are some questions that I want you to have in mind and be able to answer by the time we finish our lecture. The first one is, what does heterogeneous mean at the molecular level? Question mark. Okay. What does homogeneous mean at the molecular level? What are the properties of a solution? Okay. What is a solvent and what is a solute? How do they relate to each other? What is solubility? And what factors affect solubility and how? So, with those in mind, let's get started with Chapter 16. Okay, we're back. And this is P-Dog Does Science with this Chapter 16 Solutions lecture. So we'll start with the nature of solutions. Solutions in general are mixtures. All solutions are mixtures of two different substances. Okay, mixtures. Okay, there's a number of different types. There are two different types. There are heterogeneous mixtures, which have visibly different parts. And we refer to this, or this is my term, they are telem-apartable. That means you can tell the two different kinds of things that are mixed into the solution. You can tell them apart visually. So, for example, if you take a clump of dirt and you mix it up with water and shake it up really well, you can still see the particles of dirt and little shiny pieces and stuff like that, aside from the water that it's all mixed in. Okay, then there's the other kind, which is the homogeneous. In a homogeneous solution, the parts can't be distinguished from each other. And a homogeneous mix is also called a solution. So you can make, for example, milk. Milk is a homogeneous solution. In fact, if you have homogenized milk, what they've done is made it even more homogeneous by sticking it in a blender and mixing everything up. Okay, so the definition of our solution is this. It is a homogeneous mixture of two or more substances in a single physical state. For example, Kool-Aid or air, or soda pop or sterling silver, where the air and sterling silver are actually a liquid, a gas and a silver portion, a gas and a solid portion of versions of the solution. Right? And Kool-Aid and soda pop, and you guys have seen those, they're the regular solutions. However, soda pop is only a homogeneous mixture if it is not fizzing at the particular time. So if you see it in a bottle, in a contained bottle, then it's a homogeneous solution. But as soon as you open the bottle and you see the fizz come out, you can see the bubbles, therefore it would be a heterogeneous solution. Right, so we see that solutions can actually take any kind of state as long as they're all in the same physical state. Kool-Aid's a liquid, soda pop's a liquid, air and sterling silver are a gas and a solid. So it does kind of raise the question, what about ice water? We'll come back to that one maybe later. Okay, so, then how the properties of solutions. Solutions are when particles are very small, and they exist as atoms or molecules or even ions, where all the particles could pass through a filter paper. This would be coffee. Why coffee is a solution, because all of the particles in your coffee can pass through the filter. Okay, the particles are evenly distributed or mixed throughout at a molecular level. The molecules. Then we have particles that will not separate no matter how long the solution sits. So you can have coffee and it will stay black for as long as you have the coffee sitting there on your counter. It can be days and days, kind of like what happens in my house when somebody doesn't finish drinking their coffee and nobody wants to clean it up. The sugar, for example, in a sealed container of Kool-Aid will never settle on the bottom. It will stay dissolved and it will stay sweet forever. Just like Gatorade does the same thing. Okay, now, we have two different parts to a solution. We have the solute, which is the substance dissolved in a solution, and a solvent, which is a substance that does the dissolving. There can be only one solvent in a solution, and generally the most abundant substance in the solution. Soda pop, for example, is sugar, flavoring, and CO2 are all the solutes, where water is the solvent, the most abundant substance. Okay, with alcohol and water are completely mixable. They dissolve completely with each other. And so it'd be whichever one is the most abundant is the solvent. All right, solutes that have the ability to dissolve in a specific solvent are called soluble substances. That means they can dissolve in the solvent. Then we have ones that don't dissolve, and those are called insoluble substances. Now, these are not absolute things, that there are varying degrees to which things are soluble. For example, alcohol is completely soluble in water. Oil, however, is insoluble in water. Now, there isn't any solute that will dissolve in all solvents, and there isn't any solvent that will dissolve all substances. However, water is called the universal solvent because it dissolves many substances. It is polar, and a lot of other substances have basic polar properties to them, and things will dissolve. A lot of things dissolve in water. Okay, which brings us to the types of solutions we have. There are solid solutions, mixtures with a solid as a solvent. So, for example, gas in a solid. If you have a charcoal filter that you use to filter your water through, or it's primarily used for water, but there are other things that charcoal filters are used for. That's a gas dissolved in the carbon. There's liquid in a solid. For example, mercury is in silver for certain dental fillings, and that affects the rate at which the solid expands, so that when you eat something cold, it doesn't contract in your mouth and hurt your tooth, or it doesn't expand in your tooth and hurt it. And then there are solids in a solid. So most metal alloys are this kind. For example, sterling silver is copper and silver, and in alloys, our solutions are of two or more metals. For example, 14 karat gold, stainless steel, bronze, that sort of thing. Then there are gaseous solutions. And gaseous solutions are when the solvent itself is a gas, and for example, air is one of them. Now, nitrogen is a solvent in air. Be? Why would nitrogen be the solvent in air? And it's because it is the most abundant. It is the most abundant gas in the air. Then we have liquid solutions, where the solvent is a liquid, and this is the most frequent kind of solution that we're going to be dealing with. Okay, now liquid solutions, you can have a gas in a liquid, so like any kind of soda has CO2 dissolved in it. Or you can have liquid in a liquid. For example, antifreeze, ethylene glycol, does dissolve in water. This, by the way, is nasty stuff. It is a biocide, which means it kills life. Okay, it kills life, and essentially it's a uh, poison for anything that uses glucose uh, as an energy source. All right. Uh, Other example of these solutions. Okay, we have miscible liquids, and if things are miscible, then they can dissolve in each other in all ratios. So, for example, alcohol and water can dissolve in each other at, to any degree. In fact, um, sort of what the idea of proof of alcohol is based on. There are certain alcoholic beverages that rate their strength based on their proof. And if it is zero proof, it means that there's 0% alcohol, alcohol dissolved in the water. Most hard liquors are about uh, 80 proof. They are 80 proof. Let's write this correctly, Mr. Allen. 80 proof. And that is about 40% alcohol. Okay. or it is a 3-to-2 ratio of H2O to alcohol. There's over-the-counter stuff here in California. The highest over-the-counter is 151 proof, which is 75.5%, about 75% alcohol. Other states offer uh, grain alcohol, and it's hardcore stuff. You may have heard it. It's called Everclear, and it is 180 proof alcohol, which is a 90% solution. And then you can mix alcohol all the way up to the 100%. So it is completely miscible with each other, that in any proportion you can have. So down in this range over here, you have water is your solvent. But as soon as you get higher than 50% alcohol, the alcohol is the solvent, and the water becomes the solute. All right, so those are miscible liquids. Then there are other versions which are immiscible, and that these are liquids that do not dissolve in each other in any way. For example, oil and water are completely immiscible. They will separate each other every single time. And then we can have solids in the liquid. So, for example, Kool-Aid or the sugar and flavoring in the water is actually a solid that is dissolved in the liquid. All right, and this brings us to aqueous solutions. This is any kind of solution where water is the solvent. Okay? Into aqueous solutions, generally we have electrolytes. These are substances whose aqueous solution will conduct electricity. Okay? And these are solutions with ions. They're charged particles that will go back and forth, and uh, they will actually conduct electricity. So they will the ions themselves will travel through the liquid and create an electric current when they are charged. Okay, and those include salts, acids, and bases. And this is one of the reasons why you drink Gatorade, is because they have these salt, acids, and bases dissolved in the Gatorade in order to replenish your electrolytes that you lose when you sweat. Now, non-electrolytes are solutions that don't conduct electricity. There's no ions. They're molecular in nature, and they include substances like sugars and oils and many organic compounds. So let's talk for a second about Gatorade, because that's a lot of students, or power drinks in general. Okay, Gatorade, or actually Gatorade, but by Gatorade I mean really any sports drink, but in particular the powdered one. Powdered. So where you can mix your own Gatorade. Has in it all kinds of stuff. It has sugars, it has glucose, fructose. Okay, fructose is generally your table sugar. Okay, and it equals 2 glucoses. Glucoses minus 1 H2O, minus the water. So it takes a molecule of water to separate the fructose into 2 glucoses. But it also contains potassium chloride, and it contains sodium chloride, as a couple of salts also, as well as some potassium chlorides and some phosphates also. Phosphates. Now, these two up here are sugars. Okay, and they do dissolve in water, but they stay in their molecular form as glucose and fructose. These guys down here are salts or acids, and these will separate into their potassium, chlorides, sodium, phosphates, and these help your body. These are the electrolytes that you lose when you sweat. And if you've ever tasted sweat before, I know you all have. You've all sweated, and some of it has gone into your mouth. That these electrolytes are the saltiness that you taste in your sweat, and you don't get that back in unless you replenish your system with the electrolytes. Um, And this is what allows your cells to work. When, in your muscles in particular, you have these potassium sodium channels that go inside and out of the cell. And if you start running out of and potassium and sodium in your cells, your muscles stop working. That's when you start cramping. And so that's why you start cramping. Start cramping when lose you lose your electrolytes and must replenish. Okay, and with that you drink Gatorade. Or the other thing that's frequent is you eat bananas because bananas also provide the potassium for the potassium sodium channel, and those also help prevent the cramping. So that's a little diatribe on Gatorade and why we drink sports drinks and why they actually do help, and that they were developed in order to replenish the fluids uh, for athletes. And long story is actually that Gatorade was invented at the University of Florida, and it was a special drink that they gave the Gators of University of Florida um, for after they competed, and then they marketed and called it Gatorade. All right, so how do one of these solutions form? Well, this process is called solvation. Uh-oh. We call this process solvation, the interaction between a solvent and a solute. Okay, and it's also called hydration when the solvation. It's when solvation with the solvent of water. All right, now there's some energy changes involved here, so that when things dissolve, energy will actually travel in one direction or the other. Okay, uh, if we are breaking the attractive forces that hold molecules together, or not hold molecules, hold ions together, it is going to absorb energy, and the process is endothermic. Okay, but then if we make the attractive forces, okay, attractive forces to other things, okay, then it's going to release energy, and the process is endothermic. Both of these processes occur during solvation. Okay, so what do you think happens when sodium hydroxide and ammonium nitrate dissolve? Well, I'll give you an example of both of these in class. Um, so we'll find out. Or it's going to be a spoiler alert here. Uh, so take a pause for a sec and pause for about 5 seconds, and then to fast forward another 10 seconds if you don't want to see what the answers are. All right. Uh, well, hope you fast forward longer. NaOH gets hot. NH4NO3 gets cold, and this would be exothermic, and this would be endothermic, and we'll show those in class. Okay, which brings us to solubility, and how do things dissolve? The definition of solubility, it's not just the ability to dissolve, it is to how much they can dissolve. It is the amount of solute that will dissolve in a specific amount of solvent under given conditions of temperature and pressure. All right, so how much is dissolved under certain conditions of temperature and pressure? You kind of give us back to what is the nature of a solute and solvent. Now, we know that likes dissolve likes. In other words, which means polar solvents will dissolve polar or ionic solutes, and nonpolar solvents will dissolve nonpolar solutes. Okay, so oils will dissolve in other oils, and ionic solutions, salts and acids, will dissolve in water. Okay, now we have the effects of various effects on the solubility of various things, like for instance, temperature. If it is a solid in a liquid, the solubility will increase with an increase in temperature. Okay, now think about this. If the temperature is the average kinetic energy of molecules, okay, molecules are moving faster. Molecules move faster, increase temperature. Now, if the molecules are moving faster with an increase in temperature, that means that they are going to be colliding with the solids more and causing those solids to break up and become ions as they get into the liquid. Now, the converse is true with gases in liquids. Solubility of gases will actually decrease with an increase in temperature because the gases already have, if it's a gas and they're already moving faster, generally faster than the liquid, or they will move faster than the liquid. And if we increase the temperatures, that means the gases will, the gas molecules will find each other faster, and they will form their bubbles, and they will evolve from the liquid. Okay, and from this we have our solubility graphs that we need to see, I need you guys to look at and know how they work. So I'll show you that here in a second. All right, here's a solubility graph, and here's what it looks like. So this is the amount of grams dissolved for every 100 grams of water at various temperatures. So you can see in most of these graphs that the volume goes up as we increase the temperature. However, on some of them, for example, salt doesn't change as we increase the temperature. And terbium sulfate is actually interesting, and it's a counterexample. It actually decreases as the temperature increases. Why do you think this would happen?
Well, I'm going to let you figure out why. You should go onto Google and ask the question. Why does ytterbium sulfate decrease in solubility as the temperature increases? It's a very interesting reason. And perhaps it's a bit counterintuitive to what you guys may understand about this so far. Well, then we have factors that affect the rate of dissolving. Oh, wait a second, we actually need to finish this first part first. Um, so what are the effects of pressure on solubility? Okay, well, first one, pressure doesn't affect the solubility of most solutions, except for gases dissolved. If we're trying to dissolve a gas, then the amount of pressure on the top of the solution is going to affect the solubility. And the solubility of a gas increases as the pressure of the gas is increased over the solution. Which sort of makes sense. Think about pressure of the pressure over the top of the solution as forcing the gas into the liquid of the solution. Um, if you have more pushing onto the top of the solution, you're going to get more of it is going to give, and more of it is going to get into the solution itself. Okay, so what are the factors affecting the rate of dissolving? Okay, so these factors actually have their basis in the kinetic molecular theory from last chapter. The rate at which a substance dissolves in a solution depends on three factors. The first one is the surface area of the particle. Okay, so the particle size gets smaller, the surface area increases, which causes the interaction between the solute and solvent increasing with greater surface contact. And the smaller particles will dissolve faster than the larger ones. That's essentially what this means. But the idea behind it is when you have a solute getting dissolved into a solvent, particularly a solid solute into a solvent, the only place where you have interaction between the two substances is on the very surface. So if we get this solute here, okay, we'll say it's a square, it's like it's a salt crystal. The only place where that happens is out here on the surface of the solute, and not in here. In fact, the pieces have to get carried away after the collisions of the solvent molecules with the solute particle, which will eventually eat away till you get to the center. It's kind of like a Tootsie Roll that you have to lick away on the outside before you can get to the soft, chewy interior. But that's really what happens when you have a solute dissolving in a solvent. You have to have the external interaction before you get to the inside stuff. Okay, so the next factor that's involved is stirring. Okay, and stirring increases the interaction between solute and solvent. Okay, so if you mix them up a bit more, then the stirring or agitation will actually increase the rate of dissolving. Okay, however, this is only true for ooh, that was not good. It's only true for solids and liquids into liquid solvents. Okay, not gases. Okay, because the more you stir a gas into a solvent, the more it will come out. Okay, which brings us to the last one, which would be temperature. If you increase the kinetic energy of the particles that are in the solvent and in the solute, that increases the interaction between the solute and solvent. So next page here. Okay, which will result in a faster dissolving time, because the solvent particles will move faster and more quickly. However, once again, this only works with solids and liquids. This is not gases. In fact, it has the opposite effect with gases. And you've seen this before. What happens if you open up a hot bottle of soda? It spews out, and the gas comes out more readily. And this is because the gases already have a high kinetic energy, or they would when they are not dissolved, and they'll expand and release very quickly. Okay. Now, for saturated solution, now we need to talk about saturation, which is the next point. Saturation has to do with the solubility of a particular solute in a solvent. So, saturated solutions contain as much solute as can possibly be dissolved at existing conditions of temperature and pressure. When more solute is added, it just sinks to the bottom. Okay, this is okay. Now, we already have a term for the amount of solute that you would need in order for it to reach saturation. And it is called, right here, solubility. It is the amount of solute that will dissolve in a solvent at a specific pressure and temperature. Okay, so we talked about solubility earlier. A saturated solution contains an amount of solute that is equal to its solubility. All right. Then we have an unsaturated solution. And this is just any solution that contains less than this amount of solute that's dissolved under specified conditions of T and P. Okay. Then finally, we have the really cool one, which is called a supersaturated solution, which is a difficult word for me to say considering my S's. It contains a greater amount of dissolved solute than what's needed to form a saturated solution. Okay, which means that there's actually more stuff dissolved in the solution than can theoretically be possible to dissolve. So it's not like it's an absolute zero, absolute no, you can't get slower than that. That you can go over the saturation amount, but only under certain circumstances. Okay, and you make them by dissolving excess solute at higher temperatures and then allowing the solution to cool very slowly to prevent recrystallization. And for example, that's how we make rock candy, which we won't be able to do in here. But it's when a seed crystal is added, the excess dissolved solute precipitates out. Okay, and here is the picture of the sodium acetate that lecture refers to, right here. This is a supersaturated solution of sodium acetate, and that is a seed crystal right there. And when the seed crystal is placed into the solution, it instantly creates sodium acetate crystals, more of them, and it grows off of the seed crystal until all of it precipitates out, or all of the excess sodium acetate that is in solution precipitates out. So what is left? In fact, that is a question I'm leaving to you guys, is what is the amount of sodium acetate what is left dissolved in solution? Is it all of it? Or hold on, let me rephrase that. Okay. Does all of the sodium acetate precipitate? Does all of it precipitate out? I'll tell you right now, the answer is no. But I want you to tell me why, and I will be stamping this. If you are watching on just the video, I will be asking this question in class and stamping when you guys have an answer. Okay, so that's it for 16.1, and this is P-Dog signing out, and I'll see you guys next time.